Okay, so we continue. So by now we have already complete the study of the 2 lecture in session 3. So in lecture 1, we have studied the basics about the IoT, and by now you understand the 3 pillars underneath IoT are controller, sensor, and actuator. All right. On top of that, then you have software. All right. Then with IoT, you can implement a lot of exciting application, and in particular, we can consider robot itself as a mini version of IoT. All right. So the study from today's session is equally applicable to the implementation of a robot. And also for automation system, we could consider them as IoT. So that is a good news, all right? From the study of IoT, actually you gain more knowledge about the robot, about the automation system, all right? Then, since the 3 pillars are controller, sensor, actuator. So today's study more or less focus on the controller. In particular, how to use a controller to achieve the construction of a network, all right? Or to undergo exchange of data, all right? So lecture 2, in lecture 2, we have a study, the first basic technique, which are universal, right? So this is also good news. Once you know this technique, and you will benefit from this knowledge for your entire life, because it never change, right? This is a really basic universal technology for us to achieve data communication. So lecture 2, we have a study synchronous communication with hardware support for synchronize the byte-by-byte communication, because at the bit-by-bit communication level is always synchronized. But when we communicate the data, because conceptually the basic unit of the data is a byte, is not the bit, but only the hardware implementation is at the bit level, right? So then we need to synchronize byte-by-byte communication, okay? So the first universal method is to make use of a hardware. So we have a dedicated signal line to indicate. Okay, this is a time window for communication of a 1 byte or series of a byte. That's it, all right? Then this method has a drawback because it's costly. Because when you have one additional line, then the cost will be increased at least 25%, all right? So if you have a 4 line, okay, then it's 25% of total cost of a communication line, all right? If you only have a 2 line, then one additional line will cost you 50%, all right? Now the big question is, can we reduce the communication line into a single line, all right? That means, you see, for synchronous communication, you have a 4 line, if it's bidirectional, data line plus bit clock for the bit, another signal line for the byte. So 4 line. Then if let's say this 4 line costs you $10, can we save the cost by 75%? Remove 3 line, only have a single line. You understand what I'm talking about? The good news is yes, all right? Then if we reduce the cost by 75%, then we can achieve a long distance communication. Then we can have IoT to cover entire China. China is a big country, or IoT cover entire island of Singapore, all right, with a low cost, because Singapore is also not so small, all right? And so you see, this is always good to have this solution for low cost, long distance communication. This is why we have a second universal, okay, serial communication protocol that is called as asynchronous communication with a software format or software solution to achieve a synchronization of a byte by byte. Always remember, synchronization at the bit level is not the issue because we always want to have a synchronization at the byte level because the basic unit of the measurement of the data is a byte, not bit. All right, we talk about in terms of a byte, how many byte. Okay, so now we enter the study of lecture 3. Lecture 3 is for you to know what is a universal solution for asynchronous communication. So this is an international convention, industrial standard. All right, you just follow it. So once you know it, then you will benefit it for your entire life, right? It never change. Then at the higher level, you can do whatever you want, okay? Because the high level communication protocol are built on top of the lower level universal communication protocol. And all the microcontrollers support these two universal communication convention, right? So it's very simple, all right? Okay, then what is the basic of asynchronous communication, all right? So again, okay, you need to know why we need to do synchronized task. Then this video convince you one more time. You see the synchronization. So actually there are three devices. Okay. So there are three devices. Okay, you have 2 robots plus platform. Okay, NTU platform. So these 3 devices must synchronize, John. Okay, so that gives you strong motivation. Okay, everything must be synchronized. Then in longer distance, it's the same.
Aerial vehicle. You are about to realize your full potential. Maritime surveillance.
So if you have a mobile sensor, okay.
Crop supervision. We need to control and command the UAV in a secured way. Unmanned aerial vehicles are just like planes, but the pilot stays on the ground. The pilot and UAV must be perfectly connected at all times. Thales Alenia Space has a solution. Based on space technologies and telecommunication satellites. Using the 5 GHz frequency band allocated worldwide to aeronautical safety applications. Safe bidirectional command and control communication links are established with the UAV. From the remote pilot station through the ground gateway and the satellite payload to the UAV. Or alternatively, through terrestrial stations using the same 5 GHz frequency band and the same unique onboard terminal. Thanks to the 5 GHz system, long-range flight is now possible while maintaining permanent control on the UAV. After taking off using a 5 GHz terrestrial station, a UAV can seamlessly hand over to a satellite system for cruise, changing spot beams as it evolves in the satellite system coverage area, even possibly being handed over to another satellite while en route, in a completely transparent way, ensuring a safe command and control link available at all times from takeoff to landing. Thales Alenia Space brings to the system several orbital position and fillings that allow the transmission of 5 GHz signals in an exclusive way. Few satellites allow highly available and safe services around the entire world. The 5 GHz system is a breakthrough innovation to push further UAV applications.
Okay, so this video basically showing you two things. One is a long distance communication. Then in that case, if you need to have a full communication link, it will be very costly. All right. And the second thing that this video show you is about the wireless linkage between two communicating devices. Okay, you may have a physical wire or use electromagnetic wave to establish a wireless link, right? So, and conceptually, basically just a single line of communication, right? Instead of a 4 line, now we have a single line. Then because a reduction of a 3 line help us to save 70% of the cost, right? So that gives you the idea. Then there are many other examples. For example, in the old day, we have a fax machine. Fax machine use a telephone line. It's a single line to communicate a lot of data. Okay, you can send a fax to a remote location, right? So this is a typical application with the use of asynchronous communication. Today, you send your email, right? So email is another example. Then in the home environment, in the factory environment, we have a local network. Normally, they make use of asynchronous communication. Then in the production line, we can use RS485 protocol to build up a network of data. It's like IoT, a network of actuator, sensor, etc. Right? Okay. Now, what should be the software solution in order to achieve synchronization at the byte level? Because the transmission of a bit is always synchronized, right? As long as two devices they agree to operate at the same frequency, then because we use a shift register. Shift register for you, just imagine it's like an actuator. You take action every time you just send out the one bit, all right? Under the internal clock control. If the clock frequency is by default, we can agree, okay, at the fixed frequency and done already. So that means at the bit level is always synchronized, all right? So this is an example, okay, 4-bit parallel in. So this is a serial in, and parallel out, because all these 4-bit can be read out in parallel, all right? Here is one more example, all right? 8-bit serial in, then 1 byte parallel output. Okay, so this is quite straightforward. Then how to synchronize byte, all right? So software solution is always like this. So this is an international convention. Now we add in extra bit to indicate the start of this byte. We add in one of the 2 extra bit at the end of the transmission to indicate the end of the byte. In addition, we may or may not allocate this bit to do the error checking. Parity bit means if let's say both sides agree is an odd number of 1 or even number of 1, you just count the parity checking. If let's say here is already even number of 1, then you do not need to add in 1, right? If let's say you want to have an odd parity. Odd parity means that the number of 1 is an odd number, right? But if inside the data, number of 1 is not odd number, then you add in 1 to make the number of 1 to be odd number. So that is a usage of a parity bit, okay, for the error tracking purpose. At the receiver side, just do a verification to see whether all the data is correct or not. Okay, so this is a format. So normally is to aim start bit, parity bit, stop bit. The stop bit could be 1 or 2. If in a noisy environment, you need to aim extra stop bit. Okay, so this is a convention, right? Then in this case, at the receiver side, okay, then you will see, so he will read, okay, receiver side basically just to read, and look at the time axis. First read the start bit, then we'll read the this bit should be 001. This is the least significant bit. Okay, then there's a B0, B1, B2, etc. Then after that, he will receive the parity bit, then the 1 or 2 stop bit, etc. Right. So this is at the receive side. Then at the transmission side, right? Transmission side, you look at the time axis. First transmit start bit, then transmit bit 0, bit 1, bit 2, okay, bit 3, etc. Then parity bit, stop bit, etc. All right. So conceptually is quite simple, right? So then this slide help you to understand what is, if there's a both side, I agree to choose this odd parity. Odd parity means a number of one inside the data should be odd number. All right. Now you see, the data is like this. How many? 1, 1, 2, 3, 4, 5. 5 is odd number. Once it's odd number, then you do not need to A in any one. Okay. Then parity bit is 0. Now you see parity bit is 0. Then the total number of 1 is equal to odd number. That's it. All right. So that will help you to understand the usage of a parity bit, right? Then you may want to know, okay, if I have many bytes, because conceptually, basic unit of measurement of a data is a byte. So that means inside it's like, okay, just now I asked you to imagine the memory of a digital computer as a hotel. Hotel has a super room. Inside the super room, you have a smaller room. Each smaller room house 1 byte, all right? So that means inside hotel, you have a lot of byte. Then how to transmit out the byte? So basically, it's like this, okay? So you have a parallel transfer to this universal asynchronous receive and transmit. So UART means universal asynchronous receive and transmit, all right? Okay, so or you can say universal asynchronous receiver and the transmitter, all right? So you can do bidirectional communication. Then you see we have a series of the byte here. Then byte transfer to the buffer. Then we have a serial interface. Then this could be a shift register, all right? So you ship out to the physical line. Then is a string of a line on the, so you see the bit 0 will send out the first, followed by bit 1, bit 2. So this significant bit is a bit 0. Most significant bit is a bit 7. All right. So then transmit out. So this is the scenario of sending out the data from a computer. Right. Then what is a detail of this shift register? It looks like this. Right. So the shift register, you see, internally he has a clock. One clock appear, then this will be sent out, right? Then there's a B0 sent out, then B1 will reach the position of a B0. When next pulse come in, then B1 will be sent out, all right? So it's a shift towards the output, okay? So this slide help you visualize the action. So when every pulse come in, so that means B7 reach the B6 position. B6 will reach B5 position. B5 will reach B4 position. B4 will reach B3 position. And B0 then will reach the output line. All right. The next pulse come in, then B1 will reach the output line. All right. So then after A pulse, then the data will send out or something like that. So then for asynchronous input, let's say as a receive side, because you see if you have a 2 unit, so actually each unit has a receiver, and this also has the receiver, and the receiver, the data come from a transmitter of a unit B. There's a receiver of a unit B come from a transmitter of a unit A. So you keep this in mind. All right. Then behind this transmission, you see we always have parallel in. That is a serial output because it's transmitter. And here, once I receive, then is a serial input. I receive all the bit, but output to the CPU is parallel output. So here is the same, all right? Parallel in, then serial output, then serial input, then parallel output internally to CPU. Okay, So this help you to visualize what's going on. All right. Then at the receiver, you see first receive the start bit, then all the data bit, then the stop bit. Okay, this is one byte. Then if you have another byte, then again start bit of this byte, receive this byte, then stop bit. Okay, then you see you can receive a series of data. Okay, so this is a time access, right? Okay, for you to follow. Then this slide summarizes the working principle. So you see, it's similar to synchronous serial communication. We have it's like actuator, okay? Actually use a shift register to send out all the bit, all right? To send out the bit or receive the bit. This is a shift in register. Then we have a data register is a buffer to house one byte. Control register is for us to configure the hardware, how the hardware will perform in order to achieve a synchronous serial communication. Then status register is for the hardware to report to you what is the current working condition of the hardware, whether one byte has been received or not, etc. Then this is the physical data line. You see, we only have a single line. Okay, so in terms of a cost, okay, reduction is what? 75%. Okay, synchronous, you need to have a 4 line. This one, you need to have a single line. Reduction of a cost 75. That is a big job now. You reduce the cost by 75%. That is a tremendous, right? So this is why you need to study asynchronous, or you need to know how to use asynchronous serial communication, right? Okay, so, and by default, you will see both sides must configure to run at the same frequency. That is implicit, all right? This is to achieve synchronization of communication at the bit level, all right? Then our concern is a synchronization at the byte level, all right? Okay, that's it. So with this background knowledge, immediately you understand what is also what is output operation for asynchronous communication. For output, now you have a sender, then the sender is first send out the the start, right? A bit, then follow the data bit, then subsequently have a stop bit, then for next byte send out the start bit, then the data bit, then stop bit, etc. All right, and unit A has a transmitter, that is a sender. Unit B also has a transmitter, that is a sender. All right, it's a symmetric, right? Okay, then working principle is almost symmetric. Then in this case, this is a shift out the register. Okay, data to shift out for output operation. Then again have a buffer to hold the data to be sent out. Okay, to send out means is to write to the data line. Okay, for output operation. Then we have a control register to control it. Status register to just report what is the current status of doing data communication. Right? Again, by default, okay, both device must configure to be running at the same frequency, right? So it's quite straightforward, all right? So that's about the principle of doing asynchronous communication. Then your question is how to implement it. The good news is what all the microcontrollers have already provide the hardware implementation of asynchronous communication. Then you just need to know how to configure the hardware in order to achieve your intended synchronization at the byte level. Because as a user, you are free to choose whether you have a parity checking or not, whether it's odd parity or even parity, how many stop bit, etc. All right, and also how to set the operation frequency because by default both devices must running at the same frequency all right, so you must have know what should be the frequency to send. All right, and in addition here, because this one just sent to the single line, and actually the single line may be connected to many receiver. Then you need to know how to send out the address. Okay, let people know only the device match with the address, so just get the data, right? So it's like send the email. Your email will always go to the right destination. So just know a little bit about this. Then you will see, okay, what will be the support of a codecs, okay, for you to achieve the use of asynchronous communication. Put yourself as a user, all right? So then you will enjoy the study. Okay, why do we use microcontroller? Because we need to build up IoT, all right? So we need to know what is the microcontroller which allow us to build up a network. So remember lecture 2 with synchronous serial communication. There's a number 4. 4 means one Cortex ARM microcontroller can link up with 4 other devices. Therefore, you can have a 2-dimensional network. Okay, because you have a 4 connectivity, up, down, left, right. Then you have a matrix of IoT. That is a 2-dimensional IoT. Good news to you is with asynchronous communication, you can have a 3-dimensional IoT because this one provide you A connectivity. So actually with 6, you should be able to have a 3-dimensional IoT. Okay, so and then your role when you study the use of a microcontroller, your role is what? User. Okay, know your problem. Your problem here is what? 3 problems. One is build up the network. Second one is to interface with the sensor. Third one is what? Interface with actuator. That's it. All right. So we will study the solution to the other 2 problems in sessions 4, session 5. All right. Today's session is to know the solution, how to build, okay, and network. All right. Okay. Then actually you need to spend 1 semester to fully understand the use of a microcontroller. All right. But here with the 3 sessions, so you will gain the basic understanding about the microcontroller already. Okay. Another good news to you is as a user, you do not need to know how to design the microcontroller. All right. So you just follow instruction. Okay. If the designer tell you to use this hardware in this way, you just follow. Right. So basically, your activity is just to understand the register and know the value to be write or read from the write to or read from the register. Then use one of these 3 instructions, right? So one of these 3, not all, because they are doing the same thing. It's like how to drive a car. Actually, you just need to know 3 things. How to use a steering wheel, how to use a hand to do the control the steering wheel, how to use your leg to do acceleration, how to use your leg to do braking, yes or no? To drive a car, 3 actions, turn the steering wheel, how to brake, how to accelerate. That's it. To use microcontroller is the same. Okay, how to know the value to be write, to be read into register. Then how to use one of these 3 instructions to read the write the value. Done already. Finished. So in terms of a skill, is similar to driving a car, but only complexity is a car only have 1 steering wheel, a single one, but the microcontroller have a many registers, which is only complication. All right, and that's it. Just put yourself as a user, like when you drive a car. Okay, then you will enjoy the study of the microcontroller. All right, now here you. Okay, pay attention to this number A. Cortex M4 give you A, UART. A, actually with a 6, you are ready to build up a 3-dimensional IoT. All right. So with synchronous serial communication, you can only construct 2-dimensional IoT. But with this one, you can build up a 3-dimensional IoT. Okay. It's in front, behind, left, right, and on top at the bottom, 6, good enough. But actually, he give you A, right? It's very good. And look at the speed of communication is very fast. Okay, at the bit level, you can achieve 10 megabit per second. 10 megabit is a lot of data, right? So it's very fast enough already. Okay. Also, they give you the extra room buffer. It's like extra mega hotel room for you to house the data to be right house the data to serve as a buffer to be read, right? If let's say you are too busy, you are not able to pay attention to data communication, then all the data could be temporarily stored inside the buffer, right? So they give you a place to do the temporary storage for the buffer. And internally, it will give you the signal about the storage situation of a data into the buffer. FIFO, you just consider as a buffer, like a hotel room. FIFO means first in, first out. Okay, you have a hotel room, first in, first out, let's say, okay, that is not a big deal, right? So you have a bit for start, parity, stop, okay, in order to do synchronization at the byte level. You see, is a support. On top of that, is support wireless communication with infrared, with the use of a smart card, right? And internally, he has a direct memory access hardware support. So in this case, it will speed up the data transfer time. But this is not your concern, because as a user, you just focus on the how to configure, okay, the UART, right? That's it. So then here you see you have a such a unit, 6 of LAN is good enough for you to build up a 3-dimensional IoT. And inside the chip, you only have 64 pin for you to do physical soldering if you want to do the connection. And here you just pay attention to this number. You see 00 receiver transmitter, 11 receiver transmitter, 22, 33, 44, 55, 66, 77, right? So it means what? Actually, you have a okay, input output with other the device in the surrounding. So with the 6, you can build up a 3-dimensional network done already. All right. So this help you to see. Then if you want to do the connection, then you see on the chip is a pin 17, 18. Then how to access the data? Actually, you can also monitor the data. Is a port, because inside the program, one port is 1 byte. Each port, you remember, one port, you just imagine, is a special room, special smaller room inside the mega room. Mega room can house 4 smaller rooms. The smaller room is 1 port, all right? And each smaller room has a key. With the key, you know everything, what is inside, all right? So, and then you see physically, this pin is connect to this pin on the chip. The chip pin is over here. Just follow this, you know the pin of the chip. All right. So that give you the knowledge about how to do the physical connection. Let's say. All right. Then Cortex support this protocol. This is a typical asynchronous communication protocol convention. You see, it support. All right. Eventually, it provide 1 or 2 stop bit. All right. Stop. The bit for stop. Okay. 1 bit for start and 1 bit for parity check-in. All right. So, and the first bit to send out is the least significant bit. Last one is the most significant bit. Okay. No, this is a time access. All right. Okay. And then for the baud rate, okay. As a student, you may say for the baud rate and the communication frequency, why not just write the value, finish already, or 1,000, 2,000, 3,000. But how come ask us to do these kinds of complicated manipulation? So it's like what I say, you are the user. If you buy a car, don't question the designer of the car, all right? Because this car has been designed this way. You just know how to use it. That's it, all right? Okay, so it's the same. To set the running frequency, you need to know all this number, all right? So you have a baud rate divider. This guy has a 22 bit, 16 bit is to house the baud rate divider's integer part, and the 6 bit to house the fractional part, because the 6 plus 16 give you 22, right? But this is this 16 bit is inside this register. This 6 bit is inside is another register. Pay attention to this letter I, B, R, D. This is the F, B, R, D. They are not the same. Only this letter different, right? That's it. Okay, so don't question why design this way make our life so difficult. Okay, I don't know. Okay, actually they can just write the number, finish, right? But they want to do it, but no choice. If you buy a car, you cannot question the designer of the car, right? You just know how to use it. That's it. All right. So the clock divisor is on the formula is this one. Okay, is a system clock divided by clock divider divided by baud rate. Actually, what we want to know is this guy, baud rate. We can choose, but there's an international convention for the baud rate. Okay, you cannot choose any value. There's a set of a value, standard value. You just choose one of them. Once you get one of them, you do this calculation to get this number. Once you know this number, you split into two parts, integer part, fraction part, then you write the value inside the register. Okay, this is the transformation equation for you to convert the baud rate chosen by you among the standard value. Okay, you choose among the standard value. For example, 9,600. For those of you, you play with a fax machine, you know it a bit. By default, is 9600, right? Is one of them. Okay, then clock divisor, you can only have a two value, A16. That's it. You apply this, then get the the number. But later on, we show you example, right? So then this register just house the integer part. This register house the fractional part, right? Fractional part actually is also integer because the register can only hold integer. Then you must convert the fraction into integer. How to convert it? You see, times 64 plus 0.5. All right. I do not know very. He does not give you the equation because a fraction is like a 0.11123. Okay, but integer can only house the register only house digit in integer. So we must know how to convert decimal into integer. So do this conversion. Okay, 64 times this plus 0.5. And here showing you example. All right. So you see, 115200 is another standard baud rate we can choose. Okay, from a standard value. Then you see, once you choose this one, system clock is this one, and the clock divider you choose 16. This is chosen by you. Then you get the baud rate divider. Integer part is 10. Then it's easier. And the fractional part is 0.8507. How to convert 0.8507 into integer? Then you do this calculation. Then you get the integer. That's it. All right. Okay. So you follow this example, then you know how to do the calculation. Now we try to see how to configure. Okay, this summarize. Okay, good news to you is you have a pair of a receiver, transmitter, right, etc. Okay, and then how to use it as a user is the same. Okay, as doing configuration with synchronous serial communication. So you just configure input, configure internal process, configure output, just run it. That's it. You see, put yourself as a user, right? Then how to configure input? Input is what to receive data, right? So receive data, then you need to know what is the format of the data to be received, right? So that means by default, the data itself, but you use this word terminology like word. Okay, so word is like English, Chinese. We have a word. Okay, but data usually we talk about the byte, what is the basic unit. Okay, but use this one. Okay, to just cover the situation of a data with a 5-bit or 16-bit, something like that. So length by default it could be A, okay, it's A. Then this could be 10, etc. Whether you will enable the use of a special room, this is a buffer V4. Is you just consider special room in a hotel to temporarily store the data, all right? Whether you want to use to parity checking or not, enable, okay? But you have flexibility not to enable it. Okay, okay. The data could be 5-bit, 6-bit, 7-bit, 8-bit, okay. You see, default is 5-bit, so you must set, okay. This one you must say my data is AB, AB is 1 byte, all right, or something like that. It's quite straightforward. And okay, this one tell you, so you can implement RS-232, you build up a network. It's like you have an email, it's a network. I want my data to go to one specific location. So then you can trigger to wake up the receiver, okay, to pay attention to the data. So it means you turn on this one, and then you indicate, okay, so this data will go to this address. So this is the address. You can set up address. Let's say I am this unit is a receiver, and this unit has a list address. By default, it could be 1111. AB is 0111, but later on we have a mask to turn some 1 to be 0. Then in this case, so because it's an AB, how many possibility for you to have address? Immediately you can calculate. AB allow you to have 256 value. That means maximum number of a device you can connect together in a network. Okay. But in this case, for if let's say you want to have a dedicated network, okay, then it's 256. But for IoT, because each node you only have 6 neighbor, then 6 address will do, right? Okay, another student, okay, it's okay. So that means 6 address will do. I'm here. I have a 6 neighbor, in a 3-dimensional IoT, right? Just need to have a 6. But here, give you support of a 256. It's more than enough, right? So you turn on this one, then you say this is my address, all right? Okay, set up all these address. So you see you have a flexibility now, right? Okay. And in case if you set the 111, by default is 255. And if they say you want to have a specific address, you can use, you see there's another mask here. Okay, some bit you allow it to use. If they say you only use a 2 bit, for example, then you mask out all the rest 6 bit. You see a lot of flexibility here. Here showing you more detail about what is a 9-bit, okay, universal asynchronous read and write. So basically for each, this is for the scenario of a single bus. We may have 200 device. Then you can set the address, okay, for each of the device, okay. And this is to set the mask, to mask out a certain bit. If they say I only have a 10 device, I'm not going to use all the address bit, so you can mask them out, right? Something like that, okay. Then for internal process, so internal process, first you choose a clock source, okay. So it could be system clock and hardware clock, okay, for I/O hardware clock, all right. And here is to enable, disable, enable, because by default, each unit can do transmission, reception, whether you enable bidirectional communication, or sometimes you only have a sensor, then sensor only do one directional communication, all right, okay. So this is like this. And you see all this to enable transmission or enable transmission, okay, and enable the smart car, enable the wireless communication, and this is turn on this asynchronous communication, okay. So here just is like a software switch to switch on, switch off something. You can read the detail, okay, just for you to know. And okay, now here is how to set the baud rate you choose. If I choose this baud rate, but you may ask why not directly write this value inside the register, but you cannot directly write this. You must get this number, then have an integer part. Integer part of here is right here, all right? So right here, it's like you have a hotel super room reserved for asynchronous serial communication to house the data for this baud rate divisor. Why you have a super room? Because you have an A address, you have A key, 1, 2, 3, 4, 5, all the way to A, because 0 to 7. Once you have A key to open such a room, immediately you understand, okay? Each asynchronous serial communication has one dedicated super room to house this data. Let's say you just understand in this way. And then you have a super room to house this data. All right. Okay. Then how about the fractional divisor? Fractional divisor, you must do this calculation times this plus 0.5, you get this. Then you write this number here. That's it. Again, you have another a super room to house this data, all right, configuration data. Just imagine this way, okay. Each super room, where inside you have a 4 smaller room. Each smaller room you can house a bit 1 byte. So the super room house 4 byte. Okay, interpret in this way. And each super room has a 1 key. And the super room's 1 key plus 0 is first smaller room's key. Super room's key plus 1 is a second smaller room's key. Super room key plus 2 then is a third smaller room's key, etc. Understand? So each smaller room has its own key, all right, but is linked to the super room's key. So I explain in this way, then you immediately understand that memory is a super hotel. That's it, all right? Very simple. And I hope everyone you understand what is a hotel. Then that's it, all right? So then you see, it's not a big deal for you to understand what is a digital computer, right? Okay, very simple, right? Then how to clear the register. So to clear register basically is to write the one, write any value to clear all this bit, right? So this is because you have a receive status, okay? Because the hardware will report you the condition. It's like interrupt. Remember, once you pay attention to the interrupt, always remember to clear the interrupt, right? It's like otherwise you will have dangerous behavior. It's like your stomach tell your brain that you are hungry, then your brain go to a restaurant to take lunch. And if your brain forgotten to clear this signal from your stomach, then once you exit the restaurant, then suddenly you will enter restaurant again because your brains discover the hungry signal is still there. You forgotten to clear. Then you eat the second lunch. If you still do not clear the signal of being hungry, once you exit the restaurant, then you enter again. Then you eat the third lunch. After a few lunch, I guess you will die already. Yes or no? All right. If your brain operates in that way, you will die. All right. It's the same. So also this is a very simple operation, but it could be dangerous, like when you take your lunch. Okay. After taking your lunch, you must clear the interrupt. You say, okay, you are no more hungry. All right. But here is the same. Once you pay attention to any internal signal, remember clear it. All right. Okay. Then for output is more or less symmetric to input. Okay. Then it's the same as output. What is the size of a data? Whether you want to turn on the parity checking or not. How many stop bit? Whether it's a 1 bit for stop or 2 bit for stop, etc. All right. And it's more or less a symmetric, so you can read all this. Okay. And this one is okay to decide, because we have a special room to house the data for transmit and receive, and we want to let this special room to automatically generate signal. Interrupt means the internal signal by hardware, to generate the signal for hardware to know how to generate the signal. One way is when the special room is empty, must tell the brain. When the special room is half full, you must tell the brain. When the special room is full, then you must tell the brain. Or when the special room is has only 3/4 of the data, or 7/8 of the data. You see, you can choose all these level of data into the special room to trigger hardware. All right. So you see, you decide, then you write the value here. Then the hardware will tell the CPU, all right, or it's half full, or it's a 3/4 etc., or is completely empty, completely full. All right. So that's for this, all right. For some of the interrupt automatically generated by the hardware, and sometimes you may not want this interrupt to wake up the CPU or interrupt the working process of CPU. Then you can mask them out. But mask out does not mean don't generate the interrupt, don't generate the internal signal. Internal signal is still there, but only is don't forward this signal to CPU. That's it. All right, understand? Okay. So to mask out that means don't let the signal reach CPU. That's it. Then after that, then you run the serial communication. So the serial communication, one is what for transmitter, you just send the data. Where to send the data is here in this special room. All right. To send out the data, you have another set of a special super room in the hotel. All right. And this room also allow you to determine whether you want to enable the error signal to produce, like the overflow and some parity error, the buffer is full, etc. Error flag, whether you want to enable a special signal to be generated by the hardware or not. So you can read all these things, all right? Quite straightforward. And you then where to read all these status, because when you operate, if there's a parity check-in as an error, then the hardware will tell the CPU. So he will write the one here. It's through this register, so you can know the working condition of your hardware, etc. All right. And then status about the transmission, reception. You see whether it's busy, whether it's a buffer is full for transmission, buffer is full for reception, then you must speed up the CPU operation, etc. So you see, you can read all the hardware condition from this memory or register. And besides, okay, even when you mask out the internal signal, you can still know what are the internal signal which has been generated, which has not been reached the CPU. Okay, so you can still verify all the internal signal from this special from this register, or I use the term from this super room, all right, in the hotel, all right, etc. Okay, so detail you can read. So this is the status of interrupt or signal which did not reach the CPU, but they are still there. Okay, so you read from this super room in the hotel, all right? Okay, so it's quite straightforward. Then it's like what I say, once you pay attention to internal signal, always remember to clear this signal. It's like your stomach tell your brain you are hungry. After taking lunch, your brain must clear the signal. Then you say, I'm no more hungry. But if you do not clear it, then your brain, suddenly you see, I'm still being hungry. Let's go to the restaurant to take lunch again. Then after a few lunch, I guess you will die already. Okay, so it's the same. Okay, once you have pay attention to a signal, if you do not pay attention, do not take any action with respect to a signal, then it's okay. It's like your stomach tell you you are hungry. If you never enter a restaurant to eat, it's okay. You let the last signal to be there. All right. It's only when you take action or pay attention to it, then after that you must clear it. All right. Otherwise, you will repeatedly doing action. Then that action will make you die. All right. If you keep eating lunch continuously, I guess you will die. All right. Okay. Okay. That's all for the study of lecture 3. Okay, so in lecture 3, you know what is the working principle of doing asynchronous communication. All right, so basically we use the software solution to achieve synchronization at the byte level, and the benefit of doing so is what to reduce the hardware cost by 75%. All right, so that is a tremendous benefit. And the good news for you is all the microcontrollers support the implementation of synchronous communication. Then we gone through the example of a Cortex M4. microcontroller, let you know how to use it. All right. And another good news for you to know is Cortex M4 allow you to have synchronous communication unit. Therefore, you can build up a 3-dimensional IoT with Cortex and microcontroller. All right. So if you use a synchronous communication, you can only build up a 2-dimensional IoT. With asynchronous serial communication methodology, you can build up a 3-dimensional IoT. All right. Okay. So that's all for today's study. So we ran out of time. So as usual, okay. So you go back to digest today's content and write down your question. And next session, we will do a short Q&A and before we enter the study of session 4, right? So at the beginning of a study of session 4, we will do a short Q&A. Okay, thank you for your attention.